The weakest link principle states that the overall safety of a circuit is determined by its weakest component. For example, the weakest link would be any load rated or wired below 15 amps. If this weak link overloads, it could cause a fire or electrical shock, even though the primary overcurrent protection, like a 15 amp breaker, is still intact. The electrical codes, such as the National Electrical Code, address the issue of weak links. Overcurrent protection devices, such as circuit breakers and fuses, must be sized to protect the smallest conductor in the circuit. Conductors must be sized to carry the maximum current expected in the circuit. Loads must be rated and wired in accordance with their intended use. In practice, it is important to consider the weakest link when designing and installing electrical circuits. Firstly, branch circuits. All loads on a branch circuit must be protected by the oct that feeds the circuit. This means that the oct must be sized to protect the smallest wire in the circuit. Secondly, receptacle circuits. Receptacles are typically rated for 15 amps or 20 amps. The circuit that feeds these receptacles must be protected by an oct of the same amperage or lower. Thirdly, appliance circuits. Appliances, such as dishwashers and clothes dryers, have their own specific power requirements. The circuit that feeds these appliances must be sized accordingly. While the weakest link principle may seem like a simple concept, it is important to consider it when designing and installing electrical circuits. By ensuring that all components in a circuit are rated and wired properly, electrical hazards can be prevented and ensure the safety of the occupants. It is always advisable to consult with a qualified electrician when working on electrical circuits. The National Electrical Code, or NEC, is a comprehensive set of standards for electrical wiring and equipment in the United States. It is updated every 3 years to reflect the latest advancements in electrical safety. It is crucial to understand several key aspects of the NEC to ensure electrical safety, especially concerning the weakest link principle. One important aspect is overcurrent protection. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. The NEC specifies the maximum size of overcurrent protection device that can be used for a particular conductor size. This is to ensure that the conductor is protected from overheating and potentially causing a fire. For example, according to NEC Table 310.15b16, a 14 American wire gauge or copper conductor with type THHN insulation, which is a common type of insulation, is typically rated for 15 amps. Therefore, it should be protected by a 15 amp circuit breaker or fuse. Similarly, a 12 AWG copper conductor with THHN insulation is typically rated for 20 amps and should be protected by a 20 amp circuit breaker or fuse. Another important aspect is conductor sizing. The NEC specifies the minimum size of conductor that can be used for a particular load. This is to ensure that the conductor can safely carry the current required by the load without overheating. The size of the conductor depends on several factors, including the ampacity of the conductor, the ambient temperature, and the number of conductors in a raceway or cable. The NEC provides tables and formulas to help determine the appropriate conductor size for a given application. For example, if you have a circuit that is expected to carry a continuous load of 12 amps, you would need to use a 14 AWG copper conductor with THHN insulation, as it is rated for 15 amps. However, if the circuit is expected to carry a continuous load of 16 amps, you would need to use a 12 AWG copper conductor with THHN insulation, as it is rated for 20 amps. Load calculations are critical. The NEC requires that you perform load calculations to determine the total current that will be drawn by all of the loads on a circuit. This is important for selecting the appropriate size of overcurrent protection device and conductors. Load calculations take into account the type of load, the voltage, and the power factor. The NEC provides detailed instructions on how to perform load calculations for various types of loads. For example, for general lighting loads in a dwelling, the NEC requires you to calculate the load based on 3 volt amps per square foot. For small appliance branch circuits, the NEC requires you to include at least two 20 amp circuits. Receptacle requirements are also important. The NEC specifies the number and location of receptacles that are required in various types of occupancies. This is to ensure that occupants have convenient access to electrical power and do not have to rely on extension cords, which can be a fire hazard. The NEC also specifies the type of receptacles that are required in certain locations, such as ground fault circuit interrupter, or GFCI, receptacles in bathrooms and kitchens. GFCI receptacles are designed to protect against electrical shock by detecting ground faults and interrupting the circuit. Appliance circuits have their own specific rules. The NEC has specific requirements for circuits that feed appliances, such as dishwashers, clothes washers, and dryers. These requirements take into account the specific power requirements of the appliance and the need for dedicated circuits. For example, the NEC requires that a dedicated 20 amp circuit be provided for a laundry area. The NEC also requires that a dedicated circuit be provided for a dishwasher. These dedicated circuits ensure that the appliances have sufficient power and are not overloaded. Grounding is crucial for electrical safety. The NEC requires that all electrical systems be properly grounded. Grounding provides a path for fault current to flow back to the source, which helps to trip the overcurrent protection device and prevent electrical shock. The NEC specifies the methods for grounding electrical systems, including the use of grounding electrodes, grounding conductors, and bonding jumpers. It's also essential to consider voltage drop. Voltage drop is the decrease in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause appliances to operate inefficiently and can even damage them. The NEC recommends that voltage drop be limited to 3% for branch circuits and 5% for feeders. The NEC provides formulas and tables to help calculate voltage drop. The weakest link principle is directly related to these code requirements. The NEC aims to eliminate weak links in electrical systems by ensuring that all components are properly sized and rated. By following the NEC requirements, you can minimize the risk of electrical hazards and ensure the safety of occupants. Here are some specific examples of how the weakest link principle applies in practice. Firstly, consider a scenario where a 15 amp circuit breaker is protecting a circuit wired with 14 AWG copper conductors. If you connect a device that is rated for less than 15 amps and has a cord with a smaller gauge wire, such as 16 AWG, the cord becomes the weakest link. If the device draws more current than the cord can handle, the cord can overheat and potentially cause a fire, even though the 15 amp circuit breaker will not trip. Secondly, imagine a situation where you have a 20 amp receptacle circuit wired with 12 AWG copper conductors. If you plug in a power strip that is only rated for 15 amps, the power strip becomes the weakest link. If the total current drawn by the device is plugged into the power strip exceeds 15 amps, the power strip can overheat and potentially cause a fire, even though the 20 amp circuit breaker will not trip. Thirdly, take a case where you have a dedicated 20 amp circuit for a refrigerator. If the refrigerator's power cord is damaged and has a frayed wire, the frayed wire becomes the weakest link. If the frayed wire comes into contact with a grounded surface, it can create a short circuit and potentially cause a fire, even though the 20 amp circuit breaker will trip. However, the damage could occur before the breaker has a chance to trip. To prevent these types of situations, it is important to carefully consider the ratings of all components in an electrical circuit. Make sure that all devices and appliances are rated for the same amperage as the circuit breaker protecting the circuit. Also, make sure that all cords and wires are in good condition and are not damaged or frayed. Always use power strips that are rated for the same amperage as the circuit breaker protecting the circuit. By following these simple precautions, you can help to eliminate weak links in electrical circuits and ensure the safety of your occupants. Furthermore, it is crucial to understand the difference between standard and continuous loads. The NEC defines a continuous load as a load that operates for 3 hours or more at a time. For continuous loads, the overcurrent protection device and conductors must be sized at 125% of the continuous load. This is to account for the fact that continuous loads can cause conductors to overheat more quickly than non-continuous loads. For example, If you have a circuit that is expected to carry a continuous load of 10 amps, you would need to size the overcurrent protection device and conductors for 12.5 amps, which is 10 amps times 1.25. This means you would need to use a 15 amp circuit breaker and 14 AWG copper conductors with THHN insulation. Another important consideration is the ambient temperature. The ampacity of a conductor is affected by the ambient temperature. The higher the ambient temperature, the lower the ampacity of the conductor. The NEC provides correction factors for adjusting the ampacity of conductors based on the ambient temperature. For example, if you have a circuit that is located in an area with an ambient temperature of 90 degrees Fahrenheit, you would need to apply a correction factor to the ampacity of the conductors. This would reduce the ampacity of the conductors and require you to use a larger size conductor to carry the same amount of current. The number of conductors in a raceway or cable also affects the ampacity of the conductors. When multiple conductors are installed in a raceway or cable, heat generated by the conductors can cause them to overheat. The NEC provides adjustment factors for reducing the ampacity of conductors based on the number of conductors in a raceway or cable. For example, if you have 4 conductors in a raceway, you would need to apply an adjustment factor to the ampacity of the conductors. This would reduce the ampacity of the conductors and require you to use a larger size conductor to carry the same amount of current. Ground fault circuit interrupters, or GFCIs, are an important safety device that are required in certain locations by the NEC. GFCIs are designed to protect against electrical shock by detecting ground faults and interrupting the circuit. A ground fault occurs when current flows through an unintended path to ground, such as through a person's body. GFCIs are required in bathrooms, kitchens, garages, and other wet locations where there is a higher risk of electrical shock. Arc fault circuit interrupters, or SIs, are another important safety device that are required in certain locations by the NEC. SIs are designed to protect against electrical fires by detecting arc faults and interrupting the circuit. An arc fault is an unintentional electrical discharge that can occur when there is damaged or worn wiring. SIs are required in bedrooms and other areas where there is a higher risk of electrical fires. Surge protection is also an important consideration for protecting electrical equipment from damage caused by voltage surges. Voltage surges can be caused by lightning strikes, power outages, and other electrical disturbances. Surge protection devices, or SPDs, are designed to divert voltage surges away from sensitive electrical equipment such as computers, televisions, and appliances. The NEC recommends that SPD be installed at the service entrance of a building to protect the entire electrical system. Finally, it is important to remember that electrical work can be dangerous and should only be performed by qualified electricians. If you are not comfortable working with electricity, it is best to hire a qualified electrician to do the work for you. A qualified electrician will have the knowledge and experience to perform the work safely and in accordance with the NEC. They will also be able to identify potential hazards and take steps to mitigate them. By understanding the weakest link principle and following the NEC requirements, you can help to ensure the safety of your electrical system and protect your occupants from electrical hazards. Remember that electrical safety is an ongoing process that requires vigilance and attention to detail. It is important to regularly inspect your electrical system for any signs of damage or wear and to take prompt action to correct any problems that are found. By taking these steps, you can help to keep your home or business safe from electrical hazards.